Welcome to the HVAC-ology experience, where we talk about all things HVAC industry, topics that are so hot, they are cool.
All right, welcome to HVAC-ology episode number 4. I am with my very lovely host, Kelly Patterson, today. Hello, Kelly.
Hello, Ryan Hudson. How are you?
I'm doing excelente. That's actually Spanish for excellent. I hope you're doing well.
I am doing quite well. I am super glad it's Friday. Super glad that it's Friday.
Yes.
And, our office has gotten a little hot lately, right? Because the weather's starting to heat up. We have just switched over to HVAC, and I was curious about the number of people in the United States who don't have air conditioning in your homes. Do you know what that percentage is?
No, is this your fun fact for the day?
Do what?
Is this your fun fact for the day?
This is my fun fact.
Okay, all right. How many people in the United States as a percentage?
As a percentage.
As a percentage. I'm going to go with we haven't introduced you, Rick, yet, but you can also chime in on this one.
Sure.
Okay. So I'm going to say 32%.
That don't have it?
That don't have HVAC. What do you think, Rick? Before
I was going to say 30%. I was going to say 30. Yeah.
You know what? It is only 12 now.
Wow.
Now that does include window units and central air, right? So there is a lower percentage of people who have central air, but now only 12% of the country doesn't have actual air conditioning in their homes. Yeah.
That is unbelievable.
Wow.
It's great. It's unbelievable.
I know, right? In 2010, I think, or 2001, many years ago, it was less than 70% had anything at all. Yeah.
Yeah. I can believe that.
Well, there's some places you just visit in the country. It doesn't matter what time of year it is. It's always kind of pleasant.
It's just pleasant, right? So they don't even need it.
Yeah. So I was listening around on some podcasts, Kelly, as we were trying to get our head around what HVAC-ology is. And man, I'm listening to some of these folks, and they spend like 40 hours of research in between their podcasts. And we spend like
5 minutes?
No, like 20 minutes. 20 minutes.
That's still quite a bit of time, though.
Yeah. But I would say we have decades of knowledge in this industry. So I feel like maybe we're adequately prepared on that front.
I feel like we are. And we know that our guests are extremely adequately prepared.
Yeah. Oh, yeah. Yeah. And what did we say that we need to make sure we did at the beginning of this episode?
I remember.
Okay, go.
Okay. So please be sure that you like or subscribe to our podcast, HVAC-ology.
Yes, because it helps more than you know, because other people will find out about it.
Right.
And then the other question that I have been fielding is who in the world is HVAC-ology's audience? And my answer to that, Kelly, is contractors, engineers, sales folks.
What kind of sales folks?
Well, I would think in our industry.
All right.
But it could be anything. You know, I've had people come over here from the medical field and all over the place. And then last but not least, technicians as well. My hope is really just anybody in the HVAC business is this is something that they can listen to and hopefully find enjoyable. Yeah. So, all right. So we've done the like and subscribe. We've realized that we don't do a lot of research in this, but we find wonderful guests.
We do.
And we know what our target audience is.
So we're getting there. Like as of episode 4, we're doing pretty good, I think.
We are. Yeah. Yeah. I'm very proud of you. I'm very proud of me. Yeah. Yeah. We've done a lot. Good for us.
We're killing it. We're out there killing it.
So today we have as our guest, Mr. Rick Schnarr. And Rick Schnarr and I go way back.
Yep, that's right.
A lot of people don't know this, but he and I worked at Carrier Corporation many moons ago, and I really came to like Rick, appreciate him, both his knowledge and his just ability to really provide a solution for the customer. And it always stuck with me what his capabilities were. And, he's since left. I think he went over to Johnson Controls for a little while.
Yeah, I was there for about 6 years. Yes, exactly.
Well, I don't want to spoil anything. So
that's okay. Yeah.
The question that I like to ask folks when they've come on with us is, take us from the day, that pretty day, and maybe a May that you graduated high school, all the way up until today, and kind of walk us through that, like, high level. How in the world you get from high school, having no idea what you're going to do probably, all the way up to this? Ready,
Yeah,
set,
I had no
go.
idea. You're right. Exactly. I had no idea. So, well, thank you, Ryan. It was a great pleasure to see you again after all those years working together, and then landed in the same spot. So that's great. I came to Hoffman about a year ago. But in 1975, I left a little town in southern Indiana, a little farming community. I was a pig farmer in Indiana. And my wife says it's the best witness protection program she's ever seen. I'm sure why, but she doesn't say that. So, but I left there and joined the Navy. I spent 6 years on a nuclear-powered submarine based out of Pearl, back right in the middle of the Cold War between 75 and 81. So that's how I actually got started in this industry. I was kind of like an underwater millwright, right? Air conditioning, hydraulics, pneumatics, refrigeration, anything that wasn't attached to the nuclear power plant was my responsibility. So also was a ship's diver, among other things. So left the Navy, went to work for a small distributor in southern Indiana, in Evansville, a Bryant distributor way back in the day. Started working on the parts counter, became a residential salesperson, then became a commercial salesperson, and then the branch manager eventually. And then since then, I've really moved up from, into more sales management for some of the larger organizations. I worked for Train for several years, and had the lucky enough to actually live and work in Hawaii for about 7 years, which wasn't all bad. So
that's terrible.
It was it was hard being me out there. So, but beyond that, and then I really worked for Johnson Controls in a lot of senior leadership roles, and then I was asked if I would be interested in moving to Virginia and to help Hoffman with growing their markets in the state of Virginia. So I've been in the business almost 46 years, and it's been from residential to commercial to heavy applied. I even worked for people who developed VVT back in the early 80s for Carrier. And so I kind of got my start there, really, cut my teeth with a lot of that stuff with controls back in the early 80s. So that's kind of how I got where I'm at. Now I'm helping Hoffman grow the business in the Virginias. So I'm glad to be here.
Very cool.
Yep.
Yeah. One of the things I've always appreciated about you, Rick, is that I can tell that you take the time to really know what it is that you're trying to offer your clients. In the sense that, Kelly, we were up in Virginia recently, and I just asked Rick if he could do a high level review of just a bunch of different product lines, because we have a lot of young people in our industry that work with us. And he's like, no problem. And the fact that he could go in and talk to just every aspect of those products was very impressive to me, Rick.
I appreciate that. Thanks. It's plus comes with a lot of gray hair and stepping on a lot of rakes in my lifetime. So it's okay.
Stepping on a lot of rakes.
A lot of stepping on a lot of rakes. Yeah.
Very good.
Yeah.
That's fantastic.
Well, two topics I've always wanted to talk with you about, Rick, is series counterflow and heat recovery. And I'll let you pick. Which one do you want to start off with discussing?
Well, let's talk a little bit about heat recovery first, because that seems to be in today's markets, in today's industry, the direction of electrification, decarbonation, the reduction of fossil fuels, it became a huge opportunity for both energy savings and also to be environmentally responsible, right? So, go ahead. Sorry, you have a question, Ryan?
I was going to say, maybe to start off with the listeners, for the person that doesn't know what heat recovery is, maybe let's
Sure.
dial in what is exactly heat recovery.
So heat recovery can come in several fashions, if you will, right? If you think about it, it's really about recovering heat that's being wasted either to the ambient or the outside, and recovering that heat and then putting to use somewhere else in the building or in the system. Ideally, most systems, when you look at energy recovery, it's typically measured in something called coefficient of performance. In other words, how efficient are you in removing or taking heat from where it's being wasted and putting it somewhere where it's actually valuable and useful to reduce energy costs? That's the whole point of it, is to reduce energy costs, and also then in such a way that doesn't make a whole complicated means of getting there with a lot of fancy controls, those kind of things. Can be as basic as picking up heat and exhaust, right? And then transferring it to heating for outside air into the building, right? So it's really about moving heat from one space or energy from one location and then reusing it somewhere else, and through an efficient means of doing that. And there's several ways to do that, right? So it's really just that energy recovery is just recovering any energy you can to reuse it versus getting it wasted somewhere where it can't be used.
I like
Right.
that you said that, so my background, as you know, is physics. And so
Yeah,
one of the things that people don't appreciate is heat is energy. And what
yep,
what is cold? Cold is the absence of heat.
correct.
And a lot of people don't think of it that way, but it's the absence of that energy. And so
Right,
being able to
exactly.
take the energy from a building, and you can do that through the medium, like you said, of air. We're talking energy recovery, ventilation. We're also talking about anything from a medium of refrigerant, which you could look at from a VRV standpoint,
Right.
variable refrigerant volume, or you can look at it from a chill water aspect as well, to where instead of taking that, rejecting that heat energy to a cooling tower, you're now taking it and unloading your boiler inside your building.
Exactly. And if you combine the technology of heat recovery with more importantly, recently, are water to water systems like water cooled chillers, right? That in the past would reject all their heat to the cooling tower, right? If you're familiar at all with the chill water system, that you pick up heat in the building, you transfer that heat through a compressor into a condenser, and they typically then pump that heat and water out to a cooling tower where it's rejected, and then pump back into the chiller to reuse that water. So in the last 10 years, let's say, the development of heat recovery through water to water type applications has really grown.
Hmm.
Combine that then with the topic we just mentioned earlier, which was a series counterflow application, and that's when you're really talking about chillers or plants that have two or more large machines traditionally, right? So if I go back to my days in Hawaii, where most of that was hospitality, hospitals, and a lot of hotels, as you can imagine,
Mm-hmm.
right? So what do the hotels need most? Hot water,
Water.
right? For laundry and for keeping customers comfortable. So in many cases, they had a chill water system, but they also then had a separate boiler. Okay. Typically it's either steam, a steam gas-fired steam boiler, so using gas, fossil fuel to heat up hot water to steam. Okay. To then use within the building. So if there's some way you could capture the heat that you would want to use to heat for hot water for the laundry and for the kitchen and for all those things you need it for, in some way that it didn't use fossil fuel, ideally,
Yeah. Mm-hmm.
and at the same time provided an off benefit of chilled water. Okay, so that makes sense so far?
Yeah, it
So far.
does. I was going to, while you're talking, it reminds me of an example from about 10 years ago. I had a hotel customer, and what we did is they said, "Hey, we like you a lot, but we don't really need you right now as far as from a project standpoint." And what I came back with after kind of looking at their mechanical room is I said, "Hey, if I can get you something under 2-year payback, is that something of value to you?" And
Right.
I said, "Yeah, absolutely, but I don't think there's anything here." And so what I ended up providing was a pulney chiller that was sized for the minimum load for what they needed for both the hot side and the cold side. And what they found is that by unloading the most inefficient thing in your entire building, which is that boiler, it was insane cost savings for them. And it was such a no-brainer that they went from having no desire to do anything to all of a sudden this pulney chiller. And for those of you listening, a pulney chiller basically is that kind of that smaller machine inside your mechanical room. This pulney chiller was running nonstop, and it was providing you could call it free cooling or free heating, whichever way you want to go with it. But to some aspect, it was helping the entire system overall, to where, especially during those swing months, they didn't have to bring on that large machine, which is typically the biggest energy hog in your entire building, is that giant chiller. And, Rick, I don't know if you want to talk about this any, but the biggest sin that I see engineers commit is that they try to have it to where everything looks identical inside the mechanical room. They're not okay with, let's do a screw over here, let's do a centrifugal over here, and by the way, that screw is going to be this size and that centrifugal is going to be this size.
Right.
They don't map it to the actual needs of the customer. They'll just map it to where there's redundancy built in there.
Right. Well, if you look at most plants today, most chill water systems in the last 15 years or so, they made up for two or more chillers, two smaller chillers versus a large tonnage chiller in the earlier days. One for redundancy, plus most especially centrifugals are the most efficient, somewhere between 40 and 50%. Right, below 40%, 30% to become very inefficient machines. So to your point, Ryan, about the minimum load, when you had a large machine operating at a minimum load, not very efficient, right? And so if you could use a smaller machine to take up the part load efficiency of the large machine that's really primarily running at part load, and at the same time producing hot water, right, based off of the heat of compression that's coming off that small pony chiller. So if you go one step further than that with multiple machines, then we got into using one compressor on one chiller that was fixed speed. The second chiller was a compressor that had a variable speed drive on it, right? So the whole relationship there was, I'm going to have two chillers in parallel. I'm going to use the one machine with a VFD at the peak load, right? And then use steady state in between, and then use this chiller with a VFD on the part load, lower loads of the plant. Now you had a mixed energy efficiency, if you will, a system part load between those two chillers. So, and those were something really referred to as a parallel, meaning you had two machines in parallel, right, with the same type of piping arrangement. Typically, it was 54 entering, 44 degree leaving on the evaporator, 85 degree entering, 95 degree leaving on the condenser. Well, if you go one step further to that, then you look at a series counterflow arrangement. If you look at series counterflow, we talked just a minute ago about a 10 degree delta T from 55 to 45 on the evaporator, 10 degree delta T on the condenser at 95, 85. Okay. So whenever you look at any centrifugal chiller or even a variable speed screw machine, you have to be concerned about lift. Okay. And lift's a common term within the industry.
I was going to talk about that.
Yeah, and that's the difference between leaving chill water and leaving condenser water. Okay.
Yep.
So the higher the lift, the more the machine has to work, less efficient it is, right? So if you can use a series counterflow arrangement where you're taking half of that temperature difference across two machines in series, right? But the flow is in a counterflow direction between the evaporator and the condenser. Now you've saved about 25% efficiency, getting much better part load between the two machines. But they both then also need to be sized to maintain the full 10 degree delta T in case something happens to one of the machines. Okay. So in reality, a series counterflow with a centrifugal chiller, less attractive because most centrifugals don't do well on high lift. Okay. So where the business has really progressed is using a variable speed screw machine, a positive displacement machine that doesn't really care about lift. It'll run forever at high lift. If you put those in series counterflow, now you're really utilizing the best of two worlds: high lift capability with better efficiency, right, and splitting the load across the two machines. So series counterflow has been used productively in some plant designs, but it comes down to understanding what the flows need to be, what the minimum flow needs to be, and the rate of change. All
That's
those
right.
things make a difference, right?
So I had a customer that was an industrial, it was a paper mill. And what they had was is they would pull river water in and they would sit them in these pools, and then they would pull it in as they needed for their process. And they'd run it through a sand filter to kind of clean out the river
Yeah.
water. And what they came to me and they said, hey, we need this 90-degree water to come out at 45 degrees or 40 degrees for our process. And I'm like, bro, you can't do it.
Right.
And at least with the current situation where you have one machine, let me tell you about something called series counterflow.
Yeah.
And what we were able to do was take that 90-degree water, knock it down about halfway, and then take it through the second machine and knock it down the rest of the way down.
Yep.
And like you said, by doing that, the amount of work that the machine had to do, that lift, was a lot lower on each one to make it to where we could effectively get that 90-degree water down to 40 degrees. So I think for those that are listening, if you're in a situation to where you are trying to get a big delta T, basically the water coming into the machine versus the water leaving, and you're like scratching your head trying to figure out what in the world can I do, the answer a lot of times can be series counterflow if you've got the real estate for two machines.
That's correct. Yeah. And two's just the start, right? Then you could go into a series counterflow and then a series parallel counterflow arrangement, right? So, but in all reality, to your point, Ryan, series counterflow for high delta T applications is perfect. And then you combine that with something called variable primary flow.
Yep.
Right. Now you're getting the really the advantage of lower pump horsepower, right? As well as a higher delta T, or higher delta T across both machines, but half that delta T across each independent machine. So I like to talk about things in system part load, and the system part load is all the things combined, which is the pumps, the towers, and the chillers, right? Because what's connected to the plant or the building's not just the chiller; it's all the things that support it, right?
That's
so you have
right.
to make sure that the system is designed properly, with pressure drops and flow rates and minimum flow and those things, to make sure that you don't put the system in a situation where the chiller actually is less efficient because of the way you're applying it, right?
Yep.
So, absolutely.
So all of these, I am obviously the generalist, right, in this group. You guys are the experts. So the things that you're saying to me, the chillers and the cooling towers, those belong to the bigger applications, the
Right.
big hospitals and the industrial processes. Is there any opportunity for some smaller commercial spaces to utilize heat recovery?
Oh, absolutely. Yes. And so now, so we've been talking really about major systems, right? Large central plants, those kind of things, right? Heat recovery can also come in the way of airside heat recovery.
Okay.
Right. Like we talked a little bit earlier, that you're actually using an energy wheel, something that picks up, both sensible and latent heat, and transfers that savings, if you will, from the return side or exhaust side to the supply air side. So you're reducing the amount of temperature entering the building that you had to heat and cool, right? And that can start out at 200 CFM for residential.
So,
right?
but Kelly, maybe another way to put that is if you've got this building and you have to bring in fresh air. So ASHRAE, which is a governing body, requires us to have so much outside air inside of our commercial grade buildings. What you can do is you can take bathroom exhaust, and because you've already got to exhaust that anyway, and you can take the heat energy from that air and you can put it through what's called an ERV, energy recovery ventilation, and it passes through one side, and what it does is it actually pushes its heat energy without actually moving the air space. The air does not touch each other. So you don't basically, the stinky air, if you will, from bathrooms is not getting back into your system, but the heat energy from it, or the cool from it, will transfer over to the air that's coming from the outside. And so if you can knock a few degrees off of that outside air, it actually can have tremendous savings for you inside the rest of the building. Does that make sense?
Yep, absolutely.
Cool.
So even a small commercial office building could take advantage of this.
Yeah, even small packaged equipment, like even
Right.
that you use on a like a strip mall, right, or those
Okay,
kind of
yeah.
things. And if they have a lot of required exhaust, then being able to recover that air, right, to preheat the other air coming in the building
Yeah,
is just an intermediate. It's just an immediate savings. It's 70
it's a
to
no-brainer.
80% efficient. Yeah, it's really a
Yeah.
no-brainer. So, talking about this kind of brings me back to when I was about 4 or 5 years ago. I was living in the Pacific Northwest, and decarbonization, meaning the reduction of fossil fuels, right, became a huge driving factor in that market, that industry. So, and there's a lot of biomed applications up there, a lot of vivariums, a lot of labs, right, that kind of associated with that. And so, in previous to me working with this design build contractor, they were using a lot of air to water heat pumps, right? And air to water heat pumps are great. They have their applications, but in some cases, they can be a little bit prone to a lot of service. Okay. And not quite as efficient, quite honestly, as they could be. Remember, we talked earlier about COP. Well, coefficient performance is typically it's amount of heat that's being absorbed compared to the amount of heat it's generating. Okay, so let's just take an electric water heater. You use one kW of heat, which is about 3,400 BTUs, and you're going to get 3,400 BTUs of heat out of that. So that means for every BTU you use, you're going to produce 1 BTU of heat. That's called a COP of 1. Okay.
Okay.
If you use the same application but use a fossil fuel boiler or a hot water heater, it's only 80% efficient and that means it's got a COP of 0.8. So now I'm 20% less efficient than if I was using a straight electric. Okay.
Yeah.
Ideally, you want to get to about 3 or 4 times that amount to be efficient. So you want a COP of 3.5 to 4. Well, most air to water heat pumps were in that 3.5 to 4 ratio. So they were 4 times more efficient than a straight gas fired boiler. Okay. So, but again, they were set on the roof. They were somewhat prone to service. There were, things that they're different about that application. So we came up with a design where we know we had X amount of CFM of exhaust in the vivarium. Let's say we had 50,000 CFM of exhaust. Okay. We had 50,000 CFM of airflow providing air to the space. So in this case, we actually utilized a water-to-water heat pump chiller. We put a coil in the exhaust to operate as the evaporator during that mode. So I'm essentially cooling the exhaust air that I'm wasting anyway, right?
Right.
And then I'm producing hot water because now that condenser becomes the hot water coil, produce 140 degrees for the building for preheat, all things they need for hot water. Now, because I have a simultaneous heating and cooling load, you can take the COP on the cooling side, COP on the heating side, and add the two together. Now you have a COP of almost 8 times more efficient than a gas boiler. Okay.
You're like a magician.
No, I'm not sure about that. But here's a great part. Then in the summertime, we would use that same coil and exhaust now as the condenser, right? So it was rejecting heat in the exhaust that we get rid of anyway. That would normally go to a cooling tower. What do? We save water because no cooling tower usage. We reduce the size of the cooling tower, right? And we had a COP again of 8 or better. So that design became the standard for this mechanical contractor on every building he did for the next 5 years. So
wow.
And it was using a 250-ton water chiller versus much bigger system. So if I think back, I guess is probably one of the things I remember most of being able to use today's technology to turn it into something 8 times more efficient.
That's very cool.
Yeah.
The things that we're talking about today as we're discussing them. So I've operated in the Southeast, right? And one of the things that Southeast has that is glorious is that we have historically had cheap energy.
Right.
And so heat recovery didn't really make a lot of sense in situations. Series counterflow as an answer didn't make a lot of sense. But as time has gone on, I don't know about you, but I am finding that our our dollar per kW has gotten much higher in the Southeast. And so I just think across the board, you're going to start finding people needing to figure out clever ways. And I think that this is something to help us get to that next level.
Oh yeah, absolutely. And I think the use of water heat pumps and that type of applications to reduce energy use, reduce carbonization, right? Reduce abuse of fossil fuel. All things are headed that way, right? And I think in some ways, us in the Southeast are a little spoiled because the use of fossil fuels hasn't been quite, the alarm button, right? For whatever reasons. But you take some places like in the Pacific Northwest. I mean, it's almost outdated. You can't even get a fossil fuel boiler in a new installation anymore. So.
Yeah, one more thing to note, Kelly, you were talking about smaller places to where can things like this be useful. I actually had a job one time where they were going for a LEED. The building was going, I think LEED Platinum maybe. Anyway, and LEED basically is saying that this building qualifies because it is its efficiency is very high, or the cost to run it is very low. Anyway, we were looking for some LEED credit and actually figured out that if I took 2 air-cooled chillers, which you see a lot of our market moving over from water-cooled over to air-cooled, especially since air-cooled has become so much more efficient as time goes on. And not just that, but as far as from a technician standpoint, it seems like a lot more folks feel probably more comfortable working on air-cooled chillers than they do water-cooled machines. Anyway, this particular solution we provided, we actually ran the air-cooled chillers in series. And by doing that, having that lower delta T in between the two machines actually caused it to where their efficiencies shot way up.
Yeah, I bet.
Yeah. So if you're looking for that next LEED credit or something to get you over the edge, you could look at running your air-cooled chillers. And these were standard machines. There's nothing special. In fact, I think they were in-stock machines. If you run them in series and get that delta T a little bit lower on both of them, and then have a higher delta T that you're providing to the space, you can shrink down a lot of your equipment out in the building, and you can also get your efficiency and at your chiller plant.
Yep, exactly.
But you're magical too.
Exactly.
Both of you.
Yeah, magician.
There we go. Yeah, the HVAC magicians.
That's right. I like it.
Well, cool. Well, Rick, thank you so much for your time. I appreciate your
welcome.
knowledge and your wisdom. Do not be surprised if Kelly comes knocking again whenever I have a new subject to bring to you.
I'm glad to help any way I can. I appreciate the opportunity to share this.
Absolutely. So if you are listening and there is a topic that you are saying to yourself, I really wish that Kelly and Ryan would bring this up, send it to us on our social media. By the time you hear this podcast, all of that will be live. So find us on social media, Facebook, Instagram. Where else do you think it'll be, Kelly?
It will be on YouTube. It will be on LinkedIn probably too. Yeah.
So whenever you're, if you have something that you'd love for us to do, just reach out to us on social media. We will be sure to add that to the podcast. And anything else, Kelly?
I've got nothing, Ryan. I really very much enjoyed talking to Rick today, though. I might be knocking on Rick's door anytime I have any kind of questions.
God love you. Thank you. Appreciate being here.
He's great with love life questions as well.
No,
I'm
going to send all the people in my department to you then, Rick.
Listen, I'm not the poster child for that. Anybody who knows me knows that. So I'd leave that alone.
Nope, we're all coming to you. You're a magician in love and a magician in HVAC. I got you. We're good.
Yeah.
Well, very good. Well, thank you so much. And
thank you, guys.
This is the end. And make sure you like and subscribe. Take care.
Yes.
Awesome. Thank you, guys.
Bye.
Took a rocket past Saturn. Things don't seem to matter much to me anymore. Got lost inside a daydream. Get sick of all schemes they play on their machines. I lost so many words as I got older. You were the thought at your blue eyes. 20 years of staring at that freckle on your left shoulder. Who would have thought all I needed was to think of you to bring back the words inside? But you always bring me back at your blue eyes. 20 years of staring at that freckle on your left shoulder. Who would have thought all I needed was to think of you to bring back the words inside of me? I drove an hour to see you. Things just seem to matter more to me anyway. Got lost in reality, no answers to cancer, we never got to talk. Lost so many friends as I got older. Wish I had the strength to hold you a little bit longer. Always meant to write these words down. Thought all the best of you, faded in an endless sea. But you always bring me back at your blue eyes. 20 years of staring at that freckle on your left shoulder. Who would have thought all I needed was to think of you to bring back the words inside of me? You always bring me back at your blue eyes.